Hello everyone, this is Obi-Wan Pez for N-Simplex Pachinko. Wasn't actually planning on coming tonight, but figured why not. We actually got home, and thought I'd toss in a couple of things, see if anybody came in. It's probably already too late for me to start, whatever, it's fine. Alright, so I was looking at doing some Calc 2 stuff tonight. We already talked last time about finding the area between two curves, which is my chapter 2. So I am using calculus, line 2 by, see, it's not Abrams, who is it? Radulovich. I think it's going to be the primary author on this one. And this particular book is out of OpenStax. So anybody who wants to just take a look at it is free to do so. You can do it anytime you want. OpenStax.org. And you can download the book in its entirety. You can look at it online, do pretty much anything you want with it, just as long as you give them credit, refer to them as much as you can. And I will put this in chat for anybody who wants it. My institution's been using OpenStax for a little while, and we've pretty much decided to stick with it as much as we can, because it's free to students, it's free to the teachers. It just makes it that much better all around. The OpenStax books are slightly, potentially lower quality by some measurements, including there are fewer graphics and pretty things in it, but it's all written out in LaTeX, and if you're used to LaTeX, it's fairly easy to do. Fairly easy to get used to its style. So for tonight, again, we already talked about region bounded by curves. We have some f of x that's up here, and some g of x that's down here. Don't do that. And you want to find the area of the curve between A and B. And the best way to find this area here is going to be by taking the integral from A to B, and then taking f of x, the upper function, and subtracting g of x, the lower function. All right. In some cases, you may have a function which then decreases like this, and a function which increases like this. And you might just want to find, for instance, the area of the stuff that is between A and B. Again, here and here. Now, if you just did the exact same thing that we did before, where we did the integral of f of x minus g of x dx, then this is actually going to be a net area. So what I mean by that is that f minus g is going to have a positive value, but f of x minus g of x in this region is going to be negative. And we don't just want the net area, we want literally like what is the area of these two shapes put together. So what we're going to do here is take this point C where they intersect, and what we're going to do is to find the true area between these things. We're going to take the integral of f of x minus g of x dx as we go from A to C, and then add to it the integral from C to B. In this case, the upper function is actually g. So take the upper g of x, subtract the lower f of x dx. Alright, and let's suppose we have multiple functions. And again, we want the area between A and B, but this time we want this area in here. Again, we're going to come through and say that this is going to be C. And that the area here is going to be the, again, upper function of the area in question is going to be F. In this case, A to C. We're going to have F of x minus h of x dx plus integral from C to B of the upper function here is going to be g of x minus h of x dx. Okay. So I just wanted to check real quick and make sure that I got the gist of what was actually supposed to be going on in the book material here. All right. Whoa. All right, I'm freezing. What just happened? Come on, there we go. All right. And this here could also be rewritten as area is from A to B, the absolute value of f of x minus g of x. But if we remember going back a long way, every time that we were talking about absolute values, we were talking about just the strict numerical distance between these two things, so f and g as functions. So in this case, when we want just strict numerical values, f minus g, as long as it's positive, is going to be this particular calculation, and otherwise it's going to be the negative of that, so g minus f. And again, like we see that here, that's where we get f minus g is going to be positive between a and c, and f minus g is negative, therefore g minus f is positive between c and b. I guess another way you could do it is anywhere it's negative, you could, instead of swapping the functions, you could swap the limits of integration. I don't typically tend to do that, just because it sometimes throws people off, but it is perfectly viable. So. Alright, in some cases we could also be looking for regions that are defined in a slightly different way. So instead of finding functions that were easily defined in terms of x, we could in fact find one that's more like this. And if we wanted to find the area of this region here, let's call this f of x is g of x. Alright, in this particular case, well, it's not terrible, we could still do it, but this is going to be some y equals d value. So some maximum value in terms of y that we have here, and then our minimum value is going to be somewhere down here, which is again where these two functions intersect each other. So this is where this is the y value such that f minus g equals 0, or that f equals g. So that gets a little bit weird to define. C is going to be defined as the place where f of x equals g of x. I guess C technically is equal to f of x and g of x, so that all works too. Anyway, so we want to know where this is true. It would actually be easier to define this instead of in terms of x, because in this particular case we'd again have to find this particular x value and then mark it off and say, okay, now we're going to do from f as the bottom to d as the top, or d minus f, between this initial value and this intermediate value, and then d minus g from this intermediate value out to the end value here, which again, we have to find these values. Now, if that is not particularly nice to do, which sometimes is a problem, so instead of doing that, we can actually solve this in terms of y. So if we find it in terms of y instead, what we can do is figure out what is the area of a bar like this. Well, if this is f of x, we can instead do this as some other function, so it's not like it completely matters here, right? Because we can do it however we want, but if you call this function u in terms of y, and this one function v in terms of y, then what we want is, again, the areas here of u of y minus v of y. So this distance here is going to be positive because the u of y is further along in the positive direction, minus v of y, and all of that times dy, because this is our height here, dy. And then we just have to integrate over all of the different ones that exist between y equals d and y equals c, or from low to high, c to d. C to d in terms of y. So we do have to figure out where the intersection point is, and we have to figure out where this particular d value is, but we don't need all the x values in these cases. It doesn't matter. None of it actually is going to matter for those. So if we wanted to do something like let f of x equal to the negative natural log of, negative natural log of x, g of x equals 3x minus 7. Right, these are two completely random functions. This is probably going to get ugly at the intersection point, but, you know, it's not too bad. I could have engineered this to be nicer, honestly, and made them both have zeros at the same point or something like that. Then, yeah, this would have been much nicer. Alright, so let's figure out f equals g when negative natural log of x is equal to 3x minus 7. Oh yeah, that's ugly. No actual way to solve it, right? No, I don't think so. Yeah, not so much. But we can always find our handy-dandy calculator and get a decent approximation for it. Mine, of course, is not right here. Curses. Alright. Let's get an approximation. Desmos. Alright. Negative. Natural log x. 3x minus 7. Alright. Intersection point is 2.088 by negative 0.736. And let's go with a y value of 2. Just for fun. So if instead we look at this in terms of y, we're going to get a y equals negative natural log of x, which is going to be an x equals, this is going to be negative y, it's the natural log of x, which is e to the negative y equals x. And a y equals 3x minus 7, this is off the page. No, very close. Here's going to be a y plus 7 equals 3x, or x equals 1/3 parentheses y plus 3. Or if we feel like it, multiply it out. Y over 3 plus 1. Whichever way you feel. Alright, so then for this, we could do an integral of g of x is this one, so that is going to be y over 3 plus 1 minus e to the negative y dy from a lower bound of negative 0.736. And again, this is going to be an approximation. We're going to have to deal with it unless you have a nice, perfect value for it, like some, negative natural log or whatever that you can figure out up to positive 2. And again, if we get this to a more accurate value, we're going to get a more accurate picture for all of this, but we'll just deal with it for now. All right, so we're going to take the integral of y over 3 is going to be a 1/2 y squared divided by 3. So that's going to be a y squared over 6. Plus 1 dy dy. You take the integral, and that is a y. And then here we need a negative dy to be the du for the u up top, negative y. Therefore, if this is e to the u, then we have a du down here, and therefore e to the u du, when you take the integral, it's just e to the u. So this is a positive e to the negative y. Then we get technically a plus c. However, this is being evaluated from y equals negative 0.736 up to positive 2. We're going to take the 2 and plug it in. So this is going to be a 2 squared over 6 plus 2 plus e to the negative 2 minus parentheses a negative 0.736 squared all over 6 plus parentheses negative 0.736 plus e to the negative parentheses negative 0.736. 4/6 is going to be 2/3 plus 2 plus e to the negative second. We're just going to leave it as is for now. Here this is minus. This is going to be 0.736 squared. Is going to be very approximately a positive 0.541696 divided by 6. Okay, minus a 0.736 plus e to the positive 0.736. Okay, 2/3 plus 2, we could just rewrite that. So 2 is going to be 6/3 plus 2 is 8/3. That's e to the negative second. Minus this divided by 6 is going to be a, very approximately, 0.090282267 plus a 0.736. Plus e to the 0, nope, that's a minus. Plus e to the 0.736. Alright, this part here is a 0.64571733. Part here is going to be erase that, a negative 2.087568 5175. And there's more stuff beyond that, but whatever. 8/3 is 2.6 repeated, and e to the negative second is going to be a 0.135335 and more stuff beyond that. Alright, so when we put all of this stuff together, oh man, 8 gives us a very approximate solution of 1.36015. And that's probably as comfortable as I'm feeling of, getting this to as many decimal places as we can. Just because, again, this is approximated quite a bit. So realistically, like about 1.36 square units. And, it's also important to note, all of our values here, we're getting as positive values. So, 3x minus 7, we have this intersection point down here. Again, our x value was positive, our y value was negative. However, that was our lower bound. We were trying to find the distance that was going from so we found the y value when it went from negative 0.736 up to 2 when we're integrating on, that's it. When we're integrating on our x values, we're finding the distance between them with our u minus v in terms of y. So we wanted that whole distance there. Okay, so again, we found an area for this thing. For these two particular functions, y equals negative natural log of x, and y equals 3x minus 7, between a y value of negative 0.736 and a y value of 2. Again, an area of approximately 1.36 square units. Alright, so our next section is talking about how to find volumes of solids. So if you wanted to find, for instance, what is the volume of a cube, totally a cube, with side length 3 in all 3 dimensions. This is trivial, we've already done this before. This is just going to be volume equals length times width times height. However, if you wanted to find, for instance, the volume of a cube that has been truncated by a particular curve, something like this, roughly speaking. So this has a square cross-sectional area. However, it's been truncated by y equals, let's do something hopefully pretty easy. So let's, no, you know what, 3 is terrible. Let's do 1. Alright, negative x squared plus 1. So this is going to be pretty simple. This is just a parabolic shape that is going here. So if we were to turn this, it would look something like this. Again, 1 here, because it's, you know, totally correct. Something like that. And have a square cross-sectional area over here. And we'd want to know what area or what volume is this shape going to have. Alright, so here, this is not just going to be a simple length with height sort of thing. In this particular case, what we're going to do is we're going to say that, well, what this is basically a parabolic prism, where you have this parabolic shape here, which is then going to be dragged through a depth dimension for a distance of 1. So this is going to drag this thing backward. Like that. So really what we want here is, what is this area going to be? And then we can multiply this by our cross-sectional area going backwards. Or rather, it's not going to be the cross-sectional area, it's going to be the dimension that we have drawn this into. So because it's a prism, this is really makes it a lot easier. And in the case of a prism, you may have to choose which one's going to be the much easier version. In this case, this is going to be the much easier picture to use. So, way easier. For this particular one, so we're going to use the cross-sectional area A that we can find using calculus. The area underneath a parabola is going to end up being here. Drawn with rectangles going up like this. We want to know then the distance dx, and the height that we're going to get here is going to be negative x squared plus 1 at any given point inside of this parabola. And then our depth in this particular case is going to just be equal to 1. So the cross-sectional area in this particular case is going to be the integral of negative x squared plus 1 dx. going from 0 to 1. Again, our x values here are going to go from 0 out to 1. All that times our depth, which is going to be 1. So here, when we take the integral of negative x squared, we're going to get a negative 1/3 x cubed plus x, and again plus c, but this is a definite integral, so we don't need to do that. And multiply by 1, we're just going to get 1. Or, sorry, we're going to multiply by 1, so we're going to get just that integral portion. So x goes from 0 up to 1, which is going to end up being, plug in 1 for all these, negative 1/3 times 1 cubed plus 1 minus parentheses 0 plus a 0. Alright, plug in zeros for all these other things and they just go away. So this is going to be here a 1/3 times 1 cubed is 1, so negative 1/3 plus 1 is going to be a 2/3. Alright, then if we were to make this a little more interesting. I know, right? How could it be even more interesting? If we were to take this as a, again, square cross-section. But then this object was to shrink down. And still retain its square shape all the way down until it reaches a point. Or in fact, we can have it end at some point back here. We could take out those other pieces there. So let's go back to the larger one starts with an area of 3, and then the smaller one has an area of 1, or side length. Side lengths of 3 down to a side length of 1, and it creates this sort of frustrum shape would be what it's called. So creates this frustrum. Frustrum might be only when it's a cone. I think it's okay when you're doing it with squares, but anyway. You could probably, this is kind of an optical illusion. This is either going into the board or coming out toward you. So it's kind of interesting. Whichever way you want to look at it, it's going to be the same. So what we want to do is look at the cross-sectional area for this thing at any given moment here as it's going through. I'm going to say that as this is lying on the ground, this distance here is going to be 4. Sure, why not? So, as we go from this point here to this point here, again, a distance of 4 away, we can kind of turn this if we feel like it, and say that this is going from a height of 3 down to a height of 1, and it doesn't actually matter how you do this. So you could lay this thing down if you wanted to and let one of the sides be resting here. Actually, that does matter, doesn't it? Not really. Okay, I get it now. This is a bit like trying to find the area of a triangle that is not actually a right triangle. So whether the height is given at this nice point here, so that it is making it a right angle, or whether the entire triangle is skewed and then you're just measuring the height this way. If the height stays the same value, no matter where you're putting that triangle, you're still going to end up with the same stuff. So we can do that here, where we just kind of lay everything down. And as long as that distance between the near part and the far part is still 4, however you're going to measure it, we're going to end up with the same stuff. So, geometrically speaking, we could go this way and say, all right, we're getting okay. Geometrically, we're starting at like a y value of 3, so this is the point 0,3, and this here could be the point 4,1. Trying to find the area of this trapezoid here, which we can do by calculus by saying that we want to take the integral of this particular line. So the function here is going to be, we have a slope, this is coming down 2 and right 4, so negative 1/2 x plus 3. Dx going from 0 to 4. Alright, when we take the integral of this, we get a negative 1/2 of, one-half of negative 1/2 x squared. So this is going to be a negative 1/4 x squared plus 3x, evaluated from 0 to 4. So here this is going to be a 4 squared is 16 times negative 1/4 is going to be a negative 4, plus 3 times 4 is going to be 12, and minus zeros. So these are both zeros. So this is going to end up with a value of 8. So this is the area of this thing here, and then we take that into the depth. This is the area, which is area, and then the volume is going to be that 8 times our depth is 3. volume is going to be 24 cubic units. Whatever we were using. And that should have been here too. So if we're using inches, centimeters, whatever it might be. So 24 cubic centimeters, 24 cubic inches. Alrighty. Alright, let's see. If we did this differently. Curious, because it should work out to be the same values, but we'll see. So if this is 3, this is 1. Going like this. The overall distance is still 4, not the side length. Technically, I kind of misspoke when I was talking about that. You're not literally just laying it down. This would be like you're shifting all the material down until like all of this stuff just went straight down to here. Not physically something that could happen, but you get the idea. I hope. Alright. So if this went inward equally on both sides, so, you know, bear with my drawing, as usual. So if this is symmetric, such that the center and the center line up perfectly, and the edges all come in the same amount, and that means that the top has gone down 1, and the bottom has come up 1, if it is truly symmetric. 1 here, 1 here, and then this is a half and a half. Makes that full a 1, so 1, 2, 3. Okay, so if the bottom has come up 1 and over 4, started at 0, and let's say it's 0, negative 3 halves. Again, if we call this 0, 0, that was not brilliant. Alright, call this 0, 0. This is going to be 0, comma, negative 3 halves. This is going to be 0, comma, positive 3 halves. The end, this is going to be 4, comma, 1 half. 4, comma, negative 1 half. That one there is going to be 4, comma, 0. Alright, let's see how this plays out, because it should be the same stuff. Let's see. This is always the fun part of mathematics, is, you know, trying to figure out if the thing you think it is actually the thing that it is. That possibly made no sense to somebody. Sorry. Alright, so this is going up 1 and right 4, so this is going to be a 1/4 x minus, it's coming down, this was at, oh right, yeah, it's right there. So y equals 1/4 x minus 3 halves. This is going to be a y equals a negative 1/4 x plus 3 halves. So we want the integral from 0 to 4 of negative 1/4 x plus 3 halves minus parentheses positive 1/4 x minus 3 halves dx. So integral from 0 to 4 of. This is a negative 1/4 x, and this is a negative 1/4 x. This is going to be a negative 1/2 x. This is a 3 halves, and this is a minus negative 3 halves, so positive 3 halves again. So this is going to be a plus 3. And that we just had up above. Woo. So, since these are the same, we don't actually have to do out the mathematics because we already did it. Alright, now, what if I'm being a pain, and instead of having this exactly as it is here, I'm actually going to tip it until this becomes our bottom. This is the x-axis. Technically, that's what we're doing when we're subtracting the top from the bottom like this, but if I literally tip it, this actually affects a couple of things. So if this is going down like this is a 1. Well, first of all, that is no longer going to be straight up and down. If I tip this down, then that means that this and this side are also going to be, have to be parallel first of all, but they're going to be tipped slightly like this. That also means we're going to get 24 cubic units when we get there. Alright, so what does this mean for this stuff? Well, if we ended up literally tipping it, then you have two options. You can either do everything in terms of x still, in which case we're doing all of our slicing this way, and we're going to have to, again, break at this point here. Do the area of this part here, and then the area of this part here. That's also going to break here. So then we're going to have to do the slice here, like this. And we're also going to have to do slicing this way here. Like that. So this will break up into three different integrals. Three different integrals. One in this region, one in this region, and one in this region. Let's... okay. But it's somewhat inconvenient. So, if we just copy this over, much less carefully this time apparently, like that. We could do it in terms of y instead. Our y integrals we draw in this way. But only up until this point here. And then we would have to draw integrals, draw our rectangles this way. So this splits it up into two different integrals. So it's up to you. You can do three different integrals in terms of x, or two different integrals in terms of y. Generally speaking, I'm going to pick fewer integrals just because it's slightly easier, maybe. In this particular case, yeah. It's all going to depend on like what our angles are what, in this case, this is going to be like a sine value of, no, you're going to get a cosine value here based on your triangle that you've just drawn, and you need to get another value here. It's going to be kind of ugly. You can find it. It's not going to be terribly pretty, I don't think. In terms of y, I don't think it's actually going to be that much easier, just because now we're doing, again, this slant thing. We've got to figure out how much it's been tilted. So then everything would depend on theta. So yeah. So I'm not gonna, I'm gonna say if you can do it, arrange your objects so that something is straight, either up and down or side to side. Either one, it doesn't really matter. Once you do that, it makes everything a lot easier. Alright, I think it's my usual quitting time thereabouts. So, I've already driven today for quite a long time. My spouse and I swapped off driving. We came from upstate New York, and we're in the mid-Atlantic region, so that's a good 8-ish hours after stopping places and stretching and buying way too much coffee and sugary drinks. Let's see. Next question is, do I want to raid or do I want to just switch? Just do some gaming for a little bit. So... nostalgia. Not Sage is doing Age of Empires 2. Ah, man. Alright, that could be fun. However, I think I'm going to swap out for... okay. I think I'm going to swap out for Astroneer. The... oh no. Please don't update Steam. This is something I did not do. Alright, I'm going to switch to an Astroneer Casual. So let's see what some of the updates are. So I know that we have and because I was away, both Sea of Thieves and Astroneer need to update. Alright, touche. I deserve that. I'm going to just take a look and see what is new in the Steam stuff. So... let this be a lesson to you. Alright. That's not helping. Alright, alright, alright. Time remaining on update, 15 days, 13 hours. No, that's fine. I deserve this. 2 minutes. There we go. That's better. If there is indeed anyone out there, let me know. Rogue girl or sad girl? Let me know if you have any questions, specifically about mathematics. Maybe I should have just read it. almost there.